If you're a physical sciences student going through the regular curriculum in undergraduate and get past, say, Mathematics 1A and perhaps into 2A, you'll encounter power series. Now, if you stick with things and get into second year and take calculus, you'll get into a variety of different power series. You'll move beyond what's called Taylor series and into Lorentz series, the complex version of Taylor series. But the difference is in the existence of negative terms. If you're disinterested or uninterested in college or university, then never mind, because I'll just explain it now. If we have a function like e to the power of x or sine x, and we want to evaluate it algebraically or draw a graph of it using a computer, let's say, or even just by hand, you need to use particular x values and plot those things. But the thing is that the x values go on forever. In particular, take e. E is defined as the limit as n approaches infinity of 1 plus 1 over n all to the power of n. Or e to the power of x is defined as the limit as n approaches infinity of 1 plus x over n all to the power of n. Or alternatively, as the sum of the infinite series. So what a power series does is estimate this without worrying about the infinite number of cases. Well, e to the power of x is also defined as the function where the derivative of the function is uniquely equal to the function itself. Just as an aside, if you're new to all this, Wikipedia has an excellent page which explains various approaches. It calls them characterizations of the exponential function. But we'll stick with the one that involves limits. For e to the power of x, so long as the terms are positive, well, the expansion is known as the Taylor series, and the definition of e to the power of x is the limit shown here. But let's ignore e to the power of x for the moment and go to the slightly more difficult case, not much more difficult, but it's e to the power of x over x. Well, that 1 on x term, the x on the denominator in other words, means x to the power of minus 1, if you remember your basic algebra. This introduction of the negative term transforms our expansion from a Taylor series into what's called a Lorentz series, which often involves complex numbers. The Lorentz series expansion for e to the power of z over z, or z, that follows our convention where we use z's or z's instead of x's. That's our variables. That expansion looks like this. Negative terms introduce the possibility of poles. This is a pole for z equals 0. For that previous term, because of the hyperbolic shape of the graph, the asymptote of z equals 0, or x equals 0 on a regular hyperbola. I'll come back to that in a moment. A pole is also known as a singularity. This gets interesting as there are many different kinds of mathematical singularity. Whatever the type of singularity, it's useful to know that all singularities are discontinuities. Something unusual happens at a point of discontinuity. So, for example, the famous case of the most simple of all hyperbolas, x to the power of minus 1 or 1 over x, defined as the curve arising from that particular function, so the graph of 1 over x, has a discontinuity at x equals 0. The function is fine or well-behaved. Yes, well-behaved is indeed a technical mathematical phrase. For all values of x is less than 0 and all values of x is greater than 0. So you get a graph that looks like this. Just to underscore this and boldface it, at x equals 0 here, we have a discontinuity. Something strange is happening to that function. And so it's also called a singularity at x equals 0, at the asymptote. As the x values get closer and closer to x equals 0, then the y values are doing something very bizarre. Those are our mathematical singularities. Then there are, supposedly, possibly, physical singularities, because all those things just mentioned are a superset of the real functions, part of real analysis, which is what physical laws are actually expressed as analytical functions, things with solutions. Analytical functions are defined as being functions where they are defined and differentiable everywhere in their domain, usually for all values of x, let's say. The concept of a singularity in physics and mathematics can have a variety of meanings. I want to emphasize that again. There are different kinds of singularity. But, for example, if we define density to be mass divided by volume, which is the definition of density, and we define a physical object as anything with 0 volume but non-zero mass, like a black hole, this means that the mass vanishes into 0 space because that space becomes infinitely curved up over and again, and then we find the density becomes infinite. In quantum mechanics, we cannot say that some mass vanishes into 0 space because, well, that would imply that the Heisenberg uncertainty principle was being violated at that place. Why? Because we would be claiming something like that mass was disappearing into a region of space where the uncertainty in the position of the mass vanishes to 0, which is an impossibility in quantum theory. we would be claiming to offer perfect precision in the limits about where that mass was, something denied by the laws of quantum theory. Now, all of this exposition can serve as a window on what could be happening creatively in the minds of people. Is something being curved infinitely? Is there some hyperbolic function of the problems occupying the abstract space of a person's mind, where two contradictory theories that are incommensurate, where at x equals 0 between, say, the quantum theory of the discrete and the relativistic theory of the continuous, we have a pole? And from this is where our guesses arise, a place not well behaved, or disobedient, in other words, a place where we can finally violate Heisenberg's uncertainty. So will programming AGI require us to consider the existence of poles, hyperbolic functions, and something like singularities that exist in the expansion of certain Lorentz series? Time will tell. I propose, therefore, beginning a movement around this, following in the footsteps of something like Ernest Shackleton, who set out with little more than teams of dogs to conquer the Antarctic. I propose something similar, but with the same name: the quest for the pole. What is the analogous pole in our minds? What is mathematically undefined because there exists a function governing our creative knowledge creation? What is that function? And where is the pole from which come the ideas unpredictably? This is our quest. Join us in our acceleration towards the pole to find the most important singularity, not a purely mathematical one, or a physical one like a black hole, not an essential singularity or a technological singularity, but an epistemological one, a creative one, the singularity that can rule all others. One pole to rule them all. Okay, so in all of that, I was speaking rather loosely and only semi-seriously. I meant part of it, but the main reason for any of this is to illustrate something deeper in epistemological terms and rational terms, and by using reason. All of what I said was one big analogy where I'm invoking a number of concepts, both mathematical and scientific. Then I segued myself into wild speculation about how the human mind worked and what AGI might be. I find this way of speaking, that certain kind of pseudoscientific and mathematical patter, to be dangerous, because it can be so seductive. I have no good explanation of AGI, because I have no good explanation of personhood. I've merely got wild conjectures, mere speculation once we start getting into the details, and anyone can speculate about those. When you have a little knowledge, you can be dangerous. I think many of us could be dangerous in this regard. Indeed, we are. Gandalf said of himself in The Lord of the Rings, "And so am I, very dangerous, more dangerous than anything you will ever meet, unless you are brought alive before the seat of the Dark Lord." End quote. He was talking to Frodo, and he was trying to convey how he understood that knowledge and power meant being dangerous. But dangerous does not mean evil. It's what you do with your capacity to be dangerous that makes the difference. Iran is dangerous, but so is the USA. Indeed, the USA is far more dangerous. Eliezer Yudkowsky is dangerous. Nick Bostrom is dangerous, but so is David Deutsch and Naval Ravikant. Happily, there are dangerous people out there who are using their knowledge and resources not to deceive or spread pessimism, but to advance civilization and progress, rather than stifle either. And happily, that danger stands in contrast to those who would try and slow down progress. And the people on the side of progress are, for now, continuing to win. The good kind of dangerous people are still on the ascendancy. And likewise, I myself refuse to take that path of using one's knowledge to play the game of pretending to know more than I do, and in particular, pretending to know the future, given what I can demonstrate about what I know now. I want to understand things not yet known, so I'm not going to grift, and I'm not going to deceive. I want to speak plainly about what is known now and what is not, and do it in the open without pretending I have knowledge I do not have. One day we'll have the answers to far more of what we don't know now. We don't have to pretend we have those answers now, or are just on the cusp of having them now, in order to have them any sooner than what we will. Indeed, the pretense that we're about to find the answers to things not yet known is going to frustrate the project of learning more. We will know, which is to say, have a better explanation of where ideas come from, and hence how AGI is to be coded. It won't look like other programs, is my guess. That much we'll know. It cannot be a sequential algorithm. And my guess is it won't consist of the usual trees or loops, branching or sorting or anything like that. It won't be a recursive algorithm or a brute force searching algorithm or hashing. There'll be something else. Whatever the algorithm for AGI is, it will stand in relation to all other programs in the same way that quantum theory stands in relation to Newtonian mechanics. It won't be able to be conceived by those who are thinking only in terms of the previous worldview. This is not to say those people are incapable of seeing the truth in the better explanation, just that at a particular point in time, they don't understand how it could be possible. But when it's shown, they'll realize and they'll understand. My guess is that the program for AGI or the code or the recipe, however you want to formulate that, whatever it is the software is going to be instructing the hardware to do, when we finally have that thing, it's going to be jarring for almost every programmer and other person on the planet when they encounter this rather strange thing. Of course, they'll read it, understand it, and look back, is my guess, just as we do with all these profound discoveries, and think to themselves, how simple it was. Why couldn't they figure out the code for AGI? They'll look at it and go, that's the algorithm after all. Of course it is, the creative algorithm. And an algorithm like that will enter the standard computer science texts, or perhaps a family of such algorithms will. But until then, in the meantime, let's not pretend. Perhaps it's singularities, perhaps it's thermodynamics. But my guess is it's going to be neither purely mathematical, nor will it be physics. It won't be thermodynamics or quantum theory. It will be discussed at the level of emergence that is ideas and knowledge. In other words, epistemology. And it won't be complex. It will be simple. It will be, as always, as John Wheeler said, quote, "Behind it all is surely an idea so simple, so beautiful, that when we grasp it, in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise?"